Hello, I'm David. I'm staring up here because that's where the camera is. In case you've never seen me, now you have, and that's enough of that. So these are the requests that I've gotten. It's Maths 1M, it's Semester 1 2018. For those watching from the future, hello. These are the requests I've had to do for this revision seminar, and I will see what I can do. As usual, the video is online afterwards to those of you who are here. If you're watching this now, you've already found it, so well done. Yeah, we'll see what we can get to. I'm just going to say out loud what I've got here. I've got functions like f of x equals with a big brace here, sets of points on the complex plane, in particular things that mention the real and imaginary parts, solving complex polynomials, principal argument, related rates, induction, integration, differential equations, and trig equations. I don't know if people have a particular preference for where you would like me to start, the people who didn't put it on there. Does anyone is there some sort of consensus as to what people would prefer me to talk about first? Things that are more worrying? No one cares? Sweet. I will pick something. All right. Well, complex numbers are on my mind, so I might as well start there. And actually switch over to the document camera. Okay. Right, so I'm not necessarily going to talk about the whole complex numbers part of the course. I might do a quick summary of some thoughts that are in my head about it, and then make sure I talk about those things that are there, at least. If you have any questions along the way, if I do something that you want me to stop and talk more about, if I do something wrong in particular, that's extremely important to tell me about. Please feel free to interrupt me and ask questions. If I may say something like, yes, I'll get to that later, but if I don't, remind me later, okay? So I'm making this up as I go along, so you'll have to remind me of things that I promised I would talk about, because I might forget. Okay, so at any moment feel free to ask questions. That's what this is all about. Well, it's not all of complex numbers. I'm going to say complex numbers things, and then that means I can cover smaller bits of it. So, well, let me think. The complex numbers were originally created in order to solve cubic equations, and very soon after that it was discovered that they could be used to represent points on a plane. And from that point forward, the complex numbers have both been an algebra thing and a geometry thing. And a lot of the stuff that we do in complex numbers is exploiting the relationship between the algebra and the geometry. So, there we go. A and B in the real numbers. Complex numbers are something like a plus bi for a and b in the real numbers, and I being a number that satisfies this equation, I squared is minus 1. Technically there are two numbers that satisfy that, but we just picked one and it's I. Okay, that's what the complex numbers are, and we pretend that they satisfy all the rules that we would normally expect numbers to behave by, like being able to expand brackets and being able to multiply them in whatever order we want, being able to divide as long as you don't put 0 on the bottom, all of those things. That's basically the deal algebraically. But then they also are represented on a plane. So this point here would be a representation of the number 3 plus 2i, because it lines up with 3 on this axis and 2 on that axis. And they call that the complex plane, and some people call it an Argand diagram. think argand. I could be making that up. No, that's right. No, it's just a similar name earlier today with the medical students, which was Altman, which is not at all similar but starts with A. So I was just getting myself a bit confused. So represented on a plane like that. And so every one of these complex numbers represents a point on a plane. And that was a huge innovation when it was discovered / invented. And it's different to how the real numbers work, because the real numbers live on a line. There's a number line, and now we have these new numbers which are on a plane. And when they attempted to do that in 3D, they got all sorts of problems and caused us to create multivariable calculus. Okay, so they're represented on a plane like that, and I can find any point on that plane by locating its real part and its imaginary part. I should mention that, shouldn't I? That's called the real part. And this number here is called the imaginary part. And we have symbols for that. The real part of the complex number 3 plus 2i is the number 3, and the imaginary part of the number 3 plus 2i is the number 2. Not 2i, importantly. So it sounds like when you say imaginary part, it should be this entire piece here, but it's not. When people say the imaginary part, they just mean the number that's attached to the I and not the I itself. There is no I in the imaginary part. That's important because it makes some of the other things about complex numbers make a bit more sense. So, there are several things that we can do to complex numbers, and it's useful to know how they're done, and I'm not going to cover them all right now unless you ask later. But we can do all the things that we used to do with numbers, and then a few extra things that we didn't used to be able to do. So one of the things that we can do is we can calculate plus, and we just add them together as if they were algebra things. We can calculate minus, we can do times, we can do divide, we can do powers. Well, at least we can do powers if it's a whole positive number at the top there, actually a negative number. So we can do powers like something to the power of n, where n is an integer. We can do that sort of thing by expanding out the brackets the way we normally expand brackets, and that's pretty much it. They're all the things that we used to be able to do to numbers, and that's the things that we can now do. Some things that's missing is that we don't currently have a way of putting complex numbers in the powers, and I don't think that's covered in Maths 1M, but it is technically possible. And we have some new things. So some new things that we can do is conjugation. We can calculate the conjugate, and so if I have any complex number like that, then when I do the conjugate, which I write with a bar, then I do the opposite of the imaginary part. And it seems like a stupid thing to do, but there are very good reasons why. One of them is if you have a real number, a complex number that isn't real, and you want to multiply it by another complex number and produce a real answer, then the thing that you multiply by has to be a multiple of the conjugate. And in fact, if you want a complex number and you want to add to it and multiply by it to get a real answer, the only way to do that is to use the conjugate. It's really cool. And the other thing that's really, really cool is that you know how I said there were two choices for what I could have been? Because minus 1 ought to have 2 square roots. That's why the conjugate is the way it is. That plus or minus I, both being square roots of minus 1, causes this thing to be important. That I could have chosen my complex numbers to be upside down and use minus I instead of I, and that conjugate is holding that information about how I can switch over, and it doesn't actually change the way the numbers behave. So other things I can calculate are directly related to the geometry that I'm trying to draw with these complex numbers. So the other things I can calculate is if I have a complex number here, I can calculate how far it is from the center. Like that. So if this number here is a plus bi, then this distance here is called the length of a plus bi, also known as the modulus. And it's literally, if I draw it on the plane, it's how far it is from the origin. And I can use the geometry that I'm familiar with to calculate how long that is. It should be this. I should be able to take the two lengths that are involved there and square them and add them up and square root the answer, because that's how to calculate length on a plane. Cool, that's what modulus is. Yeah. I can also do this really cool thing, which is rotation. So complex numbers do this fabulous thing. When you multiply them, it should be that any of these operations that I do would have a corresponding picture to go with them. And there's something really cool that happens when you multiply a complex number by I. It rotates 90 degrees. I just want to show you this. Just a little interlude. Little interlude. 3 plus 2i times I is 3i plus 2i squared, but I squared is minus 1, and so I get minus 2 plus 3i. And watch what happens when I draw both of those numbers. 1, 2, 3, 1, 2. There's 3 plus 2i. And minus 2 plus 3i is here. So I had this number, and now I have this number, and they are 90 degrees apart. So when I multiplied by I, this happened. Which is really cool. So it turns out that multiplying by I rotates a complex number around the origin by 90 degrees, or pi on 2 since we're being all radians-y now. And it should seem reasonable, therefore, that if I multiply by other complex numbers, they will also produce rotations. And so now multiplication becomes about rotations, and suddenly I'm really interested in angles. I really want to know about angles that are associated with complex numbers. And so the reason why I rotates by 90 degrees is because I is already 90 degrees from the number 1. Yeah, I'll get both of those pictures on the same screen. Look. The number I is there on the y-axis. And it's already 90 degrees from 1, which is on the x-axis. And if you multiply by minus I, then you go in the opposite direction because it's 90 degrees this way from 1. And if you multiply by minus 1, you end up in the complete opposite direction because minus 1 is 180 degrees from 1. And so just from those numbers, I'm guessing that if I multiply by a number that is, I don't know, 60 degrees from 1, then it should rotate by 60 degrees. And that is the truth. I am now really interested in how far an angle, my complex number is from the x-axis in terms of an angle. So this is called the argument. So here's my complex number. And here is the argument. It's the angle from the x-axis anti-clockwise. Okay. Now here is where we get some trouble. We could rotate here, we could rotate all the way around. Like to get to I could go 90 degrees, but I could also go 450 degrees and go and end up in the same position. And so I now, when I said the argument, well, it's not really the argument, it's just an argument. Every complex number has multiple angles that will get you to the right spot. Okay, cool. So, one of the things on the board was the principal argument. So we have a note. Every complex number has many arguments. The principal argument, principal in the sense of first, meaning, principal meaning the most important. The principal argument is the shortest angle that gets to that spot. So, for example, this number here, which is going to be minus 2i, there. The shortest angle that, well, let's see. If you were measuring anti-clockwise, you would say that the angle was this. Okay? So you could say that the argument is 225 degrees, or if you like, 5 quarters of pi, because there's 4 quarters to get to here and 1 extra quarter. But the principal argument is the shortest angle that gets there, and the shortest angle is here. So an argument is this. The principal argument is here. So it's this angle, which is 180 minus, well, it's 3 quarters of pi. I don't know what the angle is to go with that. Let me think. 180 minus 45 will be 135. But it's been measured the wrong way. We're supposed to go this way to get a positive angle, so it's negative. Because negative angles go this way and positive angles go that way. And you always start from the positive side of the x-axis. That's principal argument. Whoever put principal argument up there, does that answer your question? Good. Okay. So, people have come up with multiple ways of writing. Let me just step back a bit. If I want to figure out where a complex number is, I can actually just use the angle and the modulus. If I know how far from the centre it is and how far around it is, that tells me where the complex number is as well. So that's enough information to tell me exactly what the complex number is. And people have come up with multiple notations to represent that information. So one of the notations that we have in this course is that we could say that so notation. So we have multiple notations for this, and the one in this course is that you might have something like 5, something like that, where this is the modulus and this is an argument. That's the notation in this course. But it's good to know if you're ever looking elsewhere online that the notation might be different to that. So I'm just going to put in brackets or. Some people write it like this, with an angle sign. Electrical engineers have a tendency to use that notation. So if you're ever taught by an electrical engineer, that's what they mean. Or some people use this. E to the power of I times the angle. Just so you know, if you're ever looking online and you look for this sort of thing, they are other options. In your exam, you would want to be using this one, because that's what the marker who is marking your exam is expecting to see. This is called the polar form. So because every complex number has multiple arguments, every complex number has multiple options for what its polar form could be. And because we want to have some level of consistency, we talk about the principal argument so that we can have sort of standard version. Okay. One thing I do want to say about polar form is it's not just recording the modulus and the angle. It literally is this number 5 times this number cis of pi on 3. The number cis of pi on 3 is a proper number all of its own. And it's whichever number you get to by rotating the number 1 pi on 3 anti-clockwise. Okay, so the final thing you want to be able to do is convert between polar form and standard form, Cartesian form I think they call it. In my head it's rectangular form because you draw rectangles. To convert between, well, just doing it as an example if you don't mind. Now, like that. So the cis is actually short for cos I sine. And traditionally when people write it, they put the I before the sign like this. So when they say cis, it's short for cos I sine, like that. A lot of mathematicians around the world hate cis with a vengeance. I don't know why. They really don't like it. I think it's sort of friendlier than the other notations for polar form, but I don't know, it's just probably because of the nice round letters of the C and the S, and just the way it's drawn. I don't like the pointiness of this thing, but that's just an aesthetic choice, really. Okay, so that's how you convert between them, and you would need to know what this angle, what's cos and sine of that angle is. So if I was going to convert this, that would be, damn it, 1, pi on 3 is there, 60 degrees. So cos of pi on 3 is a half, and sine of pi on 3 is root 3 on 2. So I'm getting that from this triangle here. That's a triangle that has 60 degrees in the corner here, and its lengths are 1, 2, and root 3, and that's how I remember what cos and sine of pi on 3 are. Okay, so if I really wanted this, I could multiply it out. And now it's in Cartesian form. Okay. The tricky bit is actually going the other way. It's really, this is all there is to converting between polar and Cartesian, but to convert from Cartesian back to polar, it's harder. Let me do my minus, no, yes, let's do minus 2i. So that number there, to convert from Cartesian to polar, I need to figure out an argument and I need to figure out a modulus. So the quickest way to do that is do the modulus first. Okay. So it'll be the real part squared and the imaginary part squared, and I'll add them up and I'll square root them. So minus 2 squared is 4. I'm just going to do the full version. I'm the sort of person who will just ignore the minus signs when I do this because they'll go away when I square them. Which is root 8. There you go. Fun. Okay. And you also need to figure out an angle. I'm the sort of person who will figure it out from the drawing. So it's sort of down here, and it's minus 2 this way. Maybe I don't want to use that triangle. You should probably, to get this right more often, you should probably use the triangle that goes along the x-axis first. So this is minus 2 and this is minus 2 here. So when I blow that triangle up, this angle in here I can figure out with trigonometry. That angle there, which is, let's see, tan theta would be 2 on 2, which is 1. And look, I know that what that one is. It's the same on both sides. It's half of a square, so that's 45 degrees, which is pi and 4 in radians. But the angle I'm actually looking for is not that angle. It's this angle. So therefore the argument would be pi minus pi plus pi on 4. Which is minus 3/4 of pi. So I do need to say something extremely important. You will find things in places that will say that the argument is the inverse of tan of the imaginary part divided by the real part. So you might see something like this. A plus bi you might see that. It is not true. It's only true for numbers on the right-hand side of this diagram. If the number's on the left-hand side, then your tan inverse will have to be adjusted by pi to get to the correct answer. So it's completely true that that tan of the argument is b on a, but tan inverse, especially in a calculator, is only capable of producing one angle, and there are two angles when you do tan of them that produce the answer 1, at least in the zone that you're looking at. So just be careful. Don't just go straight to tan inverse. It's safer to figure out a angle and then just check if you have to adjust it first. There you go. Cool. That's how I do it. There are other ways, but this makes the most sense to me because in my head there's a deep connection between the complex numbers and the geometry that they are able to represent. Sweet. Most people don't feel bad about this, but I do. Don't use theta as if people know what it means. Don't say theta equals as if people think that theta is the argument. Theta is just a letter. It could mean anything. Tell them that theta is the argument every time you use it. It's just good practice. If you don't do it, probably no one will care in your exam, but if you show me what I'm doing, I'm going to cringe inside because you haven't told me what the letters stand for. But that's just me. I'm a stickler for good mathematical writing. Okay, so there we go. That's polar form, which I needed to talk about in order to do principal argument. Sets of points on the complex plane. Sweet. Okay. So here's the thing. Just like in the real numbers, I can describe a set of points on the real line. So in the real numbers, I can say something like this, and I can draw a number line and go, well, here's 3 and here's 5 and it's everything from 3 to 5, not including 5 but including 3. So in real numbers I can write down some sort of statement and I can draw a set of points on the number line that that statement helps to represent. I can do that in the complex numbers too, only now my object will be, the thing that I draw will be on a plane. So I'm going to do one more in the real numbers before I move on. The absolute value of x being less than 2 in the real numbers says that, well, the absolute value of x would be just x if x is positive, and it would be minus x if x is negative. So it's a bit without the negative sign. So this would be, those numbers are less than 2, and those numbers, the absolute value is still less than 2, and that would be everything from minus 2 to plus 2, like that. Sweet. So that's the distance between x and the origin. That's what the absolute value is less than 2. And one more, just for good measure. Mate. It's minus 5. Okay, good. So the absolute value of x minus 5 is less than or equal to 3. This is a bit harder, but I can do it directly by noticing what absolute value does. So, and noticing what subtraction does. If I do x minus 5, so say x was 8, for example, 8 minus 5 is how far it is from 5 to 8. You know, I go down 5 from 8, but it's a nice way of thinking about subtraction as the distance between things. If I said, what's 20 divided by 18, not divided by, so minus 20 minus 18, you would go 2, because that's how far apart they are. So subtraction is how far apart things are, and when you do the absolute value, you don't care which one's bigger than which. So what this is telling me is that the distance, I might need to move my graph down a little. The distance from 5 to x is less than or equal to 3. That's what that says to me. And so here's 5, and everything up to 8 is less than 3. The distance from these numbers to 5 is less than 3, or equal to 3. And everything down to 2, the distance from these numbers to 5 is also less than 3. So these are all the numbers that are less than 3 away from 5. That's what this description says. Cool, huh? Okay, so now we're going to do it in the complex numbers. So in the complex numbers, if I did this, it's traditional to use z instead of x for complex numbers. So these are all the complex numbers whose length is less than 2. All right. Well, the length is how far from the centre you are. So these are all the complex numbers that are less than 2 away from the centre. I'm going to go or equal to so that I don't have to put a dotted line around the edge that I've already drawn. All of the numbers in that circle are within 2 of the centre, in a literal sense of the distance from the centre. If I measure out this way, it's 2. And that's the same idea as in the real numbers, except we've got a plane to draw the length in. And if I did this, there's the number 5. It's a real number, so it's there on the x-axis. And this is saying the distance from z to 5 is less than or equal to 3. Okay, so that means it must be less than or equal to 3 away from 5. Well, these are 3, that's 3 away from 5, that's 3 away from 5. All of this circle is exactly 3 away from 5. Conveniently, if I was just looking at the real line, it includes the drawing I drew before. Paper would be better than that. Just looking at the real line, it includes the drawing I drew before, which was from 3 to 8, but now it also has this big circle up in the complex numbers as well. Sweet. All right. I could draw. I'm going to do one more thing with this absolute value, with our modulus thing. Let's see. The modulus of z minus I is equal to the modulus of z minus 1 plus I. So let's see, that says that the distance from z to I is the same as the distance from z to 1 plus I. So I can draw that by drawing the two numbers I and 1 plus I, and finding everything that is the same distance to I as it is to 1 plus I. So the one exactly halfway between totally is going to be part of my drawing. But if I go up a bit, it's still the same distance to both of them because of this triangle here. And if I go up a bit more, it's the same distance to both because of that triangle, and I could go down a bit, and I'll get this entire line just here. And I'll use a nice light colour. Same distance between every, and no matter which point I pick here, it's the same distance to I as it is to 1 plus I. So here's a what if. What if instead of an equals there, it had been a less than or equal to? What does people think about that? Yeah? Oh no, that's just hand drawing. Sorry? Which side? This side? I'll say less than or equal to. That one? I don't know, left from right, you just have to, yeah. So, if it was less than or equal to, why don't we even draw it? That'll be useful. So this is saying the distance from z to I is less than the distance from z to 1 plus I. The distance to I is less than or equal to the distance to 1 plus I. So it's closer to this number because the distance of that number is smaller. It's closer to I than 1 plus I because the distance to I is shorter. So the distance to I is shorter than the distance to 1 plus I. And so it's closer to I, and so therefore it must be this side because it's closer. Yep. Okay, I'm going to going to say what you said so that I understand what you're saying and everyone else can hear it. Are you saying, you're saying Z take I is one down further than where Z is?
Yeah, on the imaginary axis. Is that what it's representing? Or?
Yeah, it sounds about right. So you're saying, we're saying that the length of the number which is one further down than Z is shorter than the length of the number which is 1 plus I, which is further one down and one across. Yeah.
I was just what I thought that was confusing me is that like how does I end up there? How does that?
Well, that is where the number I is. The number I is on the y-axis at position 1. And Z minus I, if Z was I, then Z minus I would be there. No, this is the axis. It's important to ask these questions. Okay. That's why colour coding is so nice. I really should have drawn this line in a different colour. Why don't we do that now for future reference? There we go. It's only marginally different on your screen, but it looks much better on my actual piece of paper. Okay, so they're all things that are talking about literal distance, but there is something else we can do. This plane here looks like an xy plane, and I can turn any information about complex numbers into information about the coordinates of the point that the complex number is. And so at any point I can always do this. I can always say that Z is x plus y I, or IY, whatever you want. I can always do that, and I use x and y to remind myself that the real part is on the x-axis and the imaginary part is on the y-axis. And I can convert any equation about z, or complex numbers, into an equation about x's and y's. So just let me do the previous one this way. So I could say that this is x plus yi minus I, and this is x plus yi minus 1 plus I. And I'll just figure out what this is as a single complex number. I'll put the y's together, the i's together. Oh, I really shouldn't be expanding out minuses and factorising at the same time. That's bad for me. Okay, so it's x plus yi minus 1 minus I x minus 1 plus y minus 1I. Okay. All right, and the length formula is this, right? If we take whatever the real part is and we square it, and the imaginary part and we square it, and we add them up and we do the square root. So we'll do that over this side too. And they're both square root, so I can, get rid of that bit. Ooh, and conveniently the y minus 1 squared is on both sides of that equation, so it's not going to make a difference to the answer. And so I just get this. And if I expand that out, I get x squared minus 2x plus 1. Oh, now there's an x squared on both sides. If I put this over here, I get 2x equals 1. X is equal to a half. Sweet. And if x is equal to a half, then, well, that's a vertical line. Yay! Which may give you some confidence if the other one feels a bit too wave your hands, nothing up my sleeves, ta-da, here's the answer. The good thing about this approach is it works for things that I haven't mentioned yet. I was exploiting what the literal meaning of the modulus is in terms of geometry. Modulus can tell you how far apart things are if you rewrite it as a subtraction. But some things don't have moduluses in them, and so I will do an example. They're supposed to be z's, right? So here's one. The real part of z has to be less than or equal to the imaginary part of 2z. I don't know why you would care, but it's a thing that I can do. I care because it gives me a sense of power over mathematics to know that I can do it. So let's see. The quickest way of dealing with this, because what does this even mean? This means that whatever it lines up with on the x-axis, that's what the real part is less than whatever twice it lines up with on the y-axis. And I can't really coordinate that in my head in terms of the geometry, and so it's quicker to just go, let z be equal to x plus yi. Technically, you're supposed to say that x and y are real, are in the real numbers, because you're supposed to declare it the meaning of any symbol that hasn't already existed in the equation. And so then the real part of z will be x. The imaginary part of 2z is the imaginary part of 2x plus 2yi, which is 2y. And so I need x to be less than or equal to 2y. I have converted my complex number inequality into a real number inequality. And now I can just treat this as if it was an x and y coordinates, because that's exactly what they are. I would prefer to write it in a way that made me feel like it was a line. So I'm just going to switch this round. And that feels more like a line equation, but with an inequality instead of an equals. So let's see. If y was equal to a half of x, it would go like that. That's where y is equal to a half of x. But y is supposed to be more than half of x, which I'm expecting to be above the line, but I'm just going to check. If I have the point 0, 1, then 1 is more than 0, so that's the correct side of the line. So it's like that. And just to be sure that I'm doing this completely correctly, I'll check it with complex numbers as well. If I choose the complex number I, the real part of I is 0, the imaginary part of 2i is 2, and 0 is less than or equal to 2. Correct. Okay, it all works with the complex numbers that are in my picture as well. So I'm just going to write that check down. If z is equal to I, then the real part of I is 0, the imaginary part of 2i is 2, and 0 is less than or equal to 2. Tick I, which is here, is inside my drawing, and so that's correct. It's on the correct side of the line. All right. Does anyone have anything to say? No, just a second. Say something. Comment or question, please. You're going to say, that was good. Good enough. I would recommend at this point, and at any time you are looking at past assignments or practice exams or tutorials or Maple TAs, to ask yourself some what-if questions. For example, I did one there earlier. You saw me do it. I went, what if that was a less than or equal to? What if that was a less than or equal to instead of an equals? Just there. What if it had been a plus I instead of a minus I? What if I had had a conjugate involved in here? Those are all questions that you could ask to start investigating more possibilities, and the more possibilities you see, the better chance you have of having done something you've already done when you go to your exam. And the better chance you have of understanding it better. Cool. All right. Well, in that case, the last thing on the complex number list was solving complex polynomials. Now, someone asked me about that on email. If you're here, what did you mean? Oh, well, telepathic, no. So, okay, I'm assuming, I don't know what that means. Does someone who is here have something they would like to ask that's more specific than that, under that heading of complex polynomials? Yes?
Yeah, I think there's an example, like a student exercise in the book.
Ooh, I have a book, thank you to my friend here. And complex numbers was like one of the most recent things we did, wasn't it? Good, so I know where I'm looking for. Okay, this is from the book. I really would prefer not to do one from your book because sometimes the people who teach the course get a little upset at me. And next semester's students will have it all done for them, and that's, yeah, whatever. So I will see if I can make one up. Before I get to that, I just want to do a little bit of a riff on this. Complex numbers are numbers, the same as real numbers are numbers. And real numbers, we used to be able to make equations out of them, and we've been doing that with our complex numbers. And polynomials are a kind of thing that we can do. We can make formulas. And in fact, the whole purpose of that complex numbers were invented / discovered for was to solve cubic equations. And it turned out that they were really good at solving quadratic equations, actually. So that's what they're for. There are polynomials. So just a second. Let's do the classic. Px is x squared plus 1. So that polynomial doesn't have any solutions. It doesn't, not wrong word, doesn't have any zeros. There are no numbers x that make this come out to 0. And that's frustrating for a lot of reasons, just because mathematicians mainly prefer a sense of completeness to things. And so what we managed to do is we managed to allow ourselves to use complex numbers, and I squared is -1, and we get 0, and the world is a better place because we can now find solutions to this polynomial that didn't have solutions before. Lovely. Okay. Where that is on the graph is a whole other story and lots of fun to try and figure out how that works, and I'm not going to talk about that today. But if you ever want to talk to me about I-planes, let me know. So that's the idea. And what I had is a real polynomial that only had real numbers to create our polynomial, and it managed to have an imaginary root. So I'm just going to write that down. Real polynomial. Imaginary root. Okay. So there's a thing that happens when you make real polynomials and you have imaginary roots. You always get the other, the conjugate of the imaginary root as well. But I'm not going to say that here on paper because it's going to obscure something that I want to say. So we were able to make polynomials with real numbers in them, and there's nothing stopping us making polynomials with complex numbers in them too, right? Completely nothing stopping us doing this. Px is x squared plus I. Nothing stopping me doing that. I can put complex numbers and numbers. I can put them wherever I want. I put them in polynomials today. Not just as things that go inside polynomials, but as coefficients in polynomials. I can do that. Okay? Traditionally, though, if you're going to allow someone to use a complex number as an answer, you normally put a z in that spot for the x. I don't care, but for the purposes of making things consistent with your courses, I'm going to do that. And now this polynomial should have zeros as well. There ought to be some numbers that when I put them in that position there and put like something squared plus I, it comes out to 0. And that's going to be a thing that we're going to have to be able to do. All right. So we want to make it come out to 0. We're going to solve z squared will therefore have to be minus I if I'm doing my algebra correctly. Okay, so I'm going to have to do the square root of negative I. As if, well, depending on whether square root means anything for imaginary numbers. So I think the quickest way to do this is via polar form. The number I has the number I is, negative I is here. And its angle is minus pi on 2. And so we've got the z squared is cis of minus pi on 2. And it's length 1, right? So I don't have to worry about putting a length in this position. Anything that's on that unit circle that goes through 1 minus 1 I and I minus I is just a plain old cis of something. Okay. Yeah. And so I should be able to divide. So de Moivre's theorem says that when you do powers of complex numbers, you just multiply the angle. And so if I do roots of complex numbers, I should divide the angle. That seems reasonable. And so I should be able to just, when I do the square root, divide this number by 2. Sweet. Only I would expect a quadratic equation to have 2 solutions, which doesn't, I've only got 1. So there has to be another one. I mean, totally, if you're going to square root things, you should do a plus or minus. But the other reason this happens is that this is not the only angle I could have used in this position here. I could just as easily have used, let's see, plus 3 pi on 2. I could have used a different argument. This one's the principal argument, but I could have used an angle going the other way, for example. I mean, if I was being very, very fun, I could go minus 1, 2, 3, 4, minus 5 pi on 2 if I wanted. And there would be infinitely many choices for what it could be. And when I divided them by 2, I would get infinitely many choices for what could have happened when I divided those angles by 2. But it turns out that all of those infinitely many choices are actually just different arguments for the same 2 numbers, which is these 2. That's a whole other revision seminar, which I can talk about if you desire. But we may want to talk about some of these other things too. I can take a vote in a minute. And so I get these 2 answers, and there's my solution. I could try and figure out exactly what those numbers were, but I can keep them as cis if I want. And so therefore, z, well, we did that. And I could try and factorize it, right? Z squared plus, plus I is going to be z minus 1 of the roots and z minus the other root. And I can leave them as cis if I want. It's a perfectly acceptable way of writing a complex number. If you're interested in knowing where these numbers are, they are on opposite sides here. And when you do square roots, they're always on opposite sides. If you do cube roots, they're always equally spaced around the circle, but there's 3 of them. All right. Yep. Okay, so that's great. So this is one of the polynomials you know how to solve. You're capable, using similar methodologies, to solve anything that's z to the power of whole number plus or minus any complex number here. And you can solve that. You can solve polynomials that have z to the whatever equals something. But what if it was more complicated than that? Give me a minute. All right, I've made up one. Hopefully it works. Always a danger making these things up on the spot in a revision seminar. Now, I hear some whisperings and I would really like to know what people are talking about because it might be relevant to everyone else who wants to know stuff. Does anyone want to voice those questions louder? Be brave? Or statements or comments that you think other people would like to hear? I'm okay with whispering. If at some point you decide to, just let me know. Okay, so this one is a polynomial, but it has some of its coefficients are not real. Two of them are real. This one's real. This one's real. That one's not real. That one's not real. So, lovely. Being a polynomial with a cube, it ought to have 3 zeros. It's possible that none of them are real. If you have a polynomial all of whose coefficients are real and it's a cubic, one of the zeros has to be real. Possibly all 3 of them, but this one, possible none of them are real. And I'm going to tell you the extra information that give me a second. So if I take out I really hope this is true. Just a second. Oh, for the sake of Frel. I'm just going to change the question. Okay. Okay, so you've got this information, and you also know that minus 3 plus 5i is a 0 of p, and you're supposed to factorize. Okay, so let's see. Well, I have multiple approaches to this. I know that since minus 3 plus 5i is a 0, that means that z minus 5 plus 3i is a factor. That's always true. If something is a 0, then x or z minus that thing has to be a factor. That's true of all polynomials, whether they're complex or real. And so I could, if I wanted to, try to figure out what the other factor was. It would be something z squared plus something z plus something, and multiply it all out and see what happens. That's one way I could do it. The other way is, knowing that this is a factor, that tells me it must be possible to factorize this to get a z minus 5 plus 3i, which is a z plus 5 minus 3i. So I can go looking for this in here. And I notice that there's a 5 minus 3i there, which is kind of useful. So that's got a z squared and that's got a z squared, and so if I remove the z squared I will get that from these first two. And that's exactly what I needed to look for, because that's what this is. And so I can go looking for this in the other half as well. Well, they've both got 2's in them, so I can take the minus 2 out. Aha! It's almost as if I set it up that way. But the point is, though, if you find one part of, if you know that this has to be a factor, and you find one part of it that has that as a factor, then the other part must have that as a factor as well. That's how algebra works. It's the same way as if you know that a whole number divides by 3, and you go, oh well, it's 15 plus something, and 3 goes into 15. Well, it must go into the other bit as well. That's how numbers work. So I know that if z plus 5 minus 3i goes into one half, and I know it goes into the whole thing, it must go into the other half as well. And so I went looking for it. And so now these both have this, so I can factorize again. Like that. So I remove this bit, that's left with a z squared. I remove this bit, I'm left with a minus 2. And now all I need to do is factorize this bit. So z squared minus 2. The quickest way is probably to make it equal to 0 and solve that, because it's a quadratic. Z squared equals 2, z equals plus or minus root 2. Sweet. And so therefore my pz must be z plus root, well, technically z minus root 2 and z minus minus root 2, because you've got to take the two answers. So just to make it look fancy, make it look nice. Those 2's are 2's and not z's. I know they look like an upside down 2, but that's just my weird ass handwriting. And now it's in linear factors because each factor only has one z in it. And it's not to a power. Okay. So let's do some what ifs. What could have happened is that instead of getting a plus 2 at this spot, I could have got a minus 2, in which case I would have gotten a plus or minus root 2i. Because when you square root something that's got a minus in it, you end up with an I. What could have happened is I could have ended up with, 2 plus 5i. Oh, sorry, I could have ended up with, 2 plus 5i, or some ridiculous thing in that position, in which case I would have to do what I would do to square root a complex number, which is to write it in polar form. So it would not be impossible. Oh, cool, I want to make up that one. Ready? I just want to do it. Yes. All right. It's subtly different. In fact, there is only one thing different about this than the one we had before. Is it now? Oh no, it is two things different. I've switched these two numbers and turned this one into a minus, into a plus. I'm extremely hoping that the same root is still there. All right, let's go. So I'm going to take a... Oh, come on. Yeah, I know. Right. I really hope I've done this right. I'm sorry if I haven't. So if I take a z squared out of this, no, I've done it wrong. Sorry, guys. It was such a good idea. I know how to fix it. Yeah. Okay. Yes. 10 points to Dumbledore. Because, of course, I am the principal of the school. Spelt. Okay. Well, that was great, except I got an I left. If I remove an I from this, I have to divide this by I. So this has already got an I, that's great, that'll become a 5. And, well, 3 divided by I, if I times the top and bottom by I will get 3i divided by minus 3i. Like that. Beautiful. And now I can factorize it. Yay! I know! This one just here? Or this one just here? Yeah, let's do that bigger. Because I should probably not put an intra-sentence exclamation mark. So it was 3 plus 5i, yep. And to remove the I had to divide by I. So that's 3 divided by I plus 5, because I can divide them separately by I. And dividing by I could multiply the top and bottom by I. Because I'm doing this. I'm trying to factorize an I, which means that I'm rewriting this as I times something. So in the same way as I try when I pull a 2, if I had a 5 there and I pulled a 2 out, it would become 2.5. Because 5 is 2 times 2.5. So it's the same as dividing, pulling a 2 out is the same as dividing everything inside by 2. So pulling an I out is the same as dividing everything on the inside by I. How's that feel? Not good? Yeah, you can think of pulling things out as the same as dividing the inside by that thing. So essentially I'm multiplying by I and dividing by I, which is the same as doing nothing. Yes, good, well done. So to divide by I can multiply the top and bottom by I, and I get 3i divided by I squared, but I squared is minus 1. So that's how I did that bit there. And now I've got this bit factorized, that's great, and I need to figure out what the solution to this is. Oh wow, look at that, that's insane. I'm going to have to divide by I again. I know what happens when I divide by I. It's the same as multiplying by minus I. We just did that back here. And if I want to solve that, I'm going to have to go to polar form. So I did it wrong because I wanted it to be the same as the one we had before when we had like just, anyway. I'm going to have to go to polar form, and it's here. It's length 2, and it has cis of minus pi on 2, or if you like, 2 cis of 3 pi on 2. And so I can, well, sorry. And so I can get, therefore, that the z is root 2 cis of minus pi on 4, or root 2 cis of 3 pi on 4. Not moving it far enough, David. And so therefore my P of Z is Z. Oh, crappity, crap of crap. I reckon there's going to be an I out the front. I made it really hard for myself and all of you. I'm very sorry. There's the fact that there's an I next to the front there. If I got something that started with like a 3x squared, and I found its roots, if I just wrote Z minus, let me just do it. If I wrote Z minus this thing, and Z minus this thing, and then there's also the Z plus 5 minus 3I. That's great. Crap. That's great, except if I multiply this out, I'm just going to get a Z squared and not an IZ squared. And it's supposed to have an IZ squared. So I need to whack an I out the front. Wow. Picked a really bad one, didn't I? No, it won't change what the zeros are, but I'm supposed to make it match up to the actual coefficients that are here. So without the I, all of this multiplies together to give something that starts with a plain Z cubed, and it's supposed to start with an IZ cubed, so I need an I out the front. But since all the zeros match up correctly, that's the only thing I need to do to fix it. Yeah, just one Z cubed. But that was my fault because I was originally trying to be extremely clever, and I should have fiddled with this one instead of that one. I'm sorry. All right. So there is at least one moral to this story, which is that sometimes when you do a what if, weird crap happens and you need some people to rescue you, like you guys rescued me. You don't feel like you did, but me having to say it aloud really helped. I wish you could talk your exam out loud, but that would be considered cheating. So don't, but you can probably pretend. But when you do your study, it's good to do some what ifs, and if you do get yourself into a quandary, feel free to drop into the Maths Learning Centre and we'll chat to you about it and see if we can fix the problem. And what came up for me here is that it's possible when you do these things for there to have to be a coefficient out the front. It might not be imaginary, it might be a 2 or a 3 or something, but it's possible. And now we know how to deal with it. We'll factorise as much as we can, find all the zeros, and then we're just going to have to put that coefficient at the front to make sure it works properly. All right, that's enough complex numbers for now, unless someone else has another question about complex numbers. Yes?
So if you assume that a polynomial's got a complex zero,
Mm-hmm. I'm just going to restate that, if that's okay. So you said you've got a polynomial with a complex 0, and you're saying you only assume the conjugate is there too if the original polynomial had all real. That's sort of what you said? That is correct. So the idea is that if you have P of X, P of Z has 1 plus 3i as a 0. If the coefficients of P are real, then that means that 1 minus 3i is a 0 too. 0 as well. If the coefficients of P aren't real, this tells us nothing. We get no new information. Yeah. Other than the fact that it is a 0 in the first place. So you can always use the fact that if it's a 0, when you sub it in, you get 0 as the answer. And you can always use the fact that if it's a 0, then the matching factor has to be there. That's always true. But if the coefficients are all real, and you get a non-real 0, then you have to have the conjugate there as well, which is extra information that you sort of get for free for the way, because of the way the real numbers and the complex numbers work. Very good to say that out loud. I think everyone needs to hear that multiple times. Thank you. All right. Well, what am I going to talk about now? I've done all the complex number things I could have done, or that I have the stamina for today. I should say there's already some videos about most of these things. So if I don't, well, I won't get to them all. Just know that on the Maths Learning Centre website there's already videos for some of these things. Things like integration, including integration by parts and induction, and, pardon me, there's at least one on related rates. I haven't done anything specifically on this. So, the person who wrote trig equations there next to differential equations, what do you mean?
That was like using them in the inverse inside another trig function and wanting to differential.
Or you have something in your head that I don't know what it sounds familiar.
So we have like, say, inverse function, and then inside the inverse function is a trig function, and then inside that is a trig function with like the derivative of it first.
Okay, I'll see if I can find it. Does anyone else have an idea of what we're talking about here? No? So it was near the differential equations, was it? All right, this is way back at functions. Aha. Yes, I've found it. That looks about right. Okay, good. It looks like, based on those two bits, that I should talk about some function stuff. Not all functions, but some functions, and I'll see if I can find the bit you want. So first I'll have a talk about the thing that's on the board there, which is functions that have those braces in them. So they're called piecewise, damn it. Piecewise functions is what I'm going to talk about first. So piecewise functions are functions that have different formulas in different places. Your classic function has the same formula everywhere. Y equals x squared. Beautiful. Always x squared. But a piecewise function has a different formulas for different x's. So and so they tend to look like this. Something like that. And so there's this big thing which is called a brace, which has the two different possibilities. Sometimes the formula for f of x is x plus 1, and sometimes the formula for f of x is 2x. And the places where those happen is that if your x is less than or equal to 0, then the formula you're using is x plus 1. And if your x is greater than 0, the formula you're using is 2x. That's called a piecewise function. And you're literally taking two other functions and tearing them apart and gluing them back together again. So just as an example of this one, f of 3 would be, so I go to here. This part wouldn't normally be on the this is in my head. It's a thought bubble. I go, well, 3 is greater than 0, so I'm going to use 2x as my formula. And so it's going to be 2 times 3, which is 6. And f of minus 3, well, I'll think again. Minus 3 is less than or equal to 0, so I'll use x plus 1. So it'll be minus 3 plus 1, which is negative 2. So that's basically how to read this formula. It tells you that when you use the formula on a number, first you check which condition the number satisfies, and then whichever one it does, you use that formula. That's how it works. And I'm just going to hop over onto the computer. This is Desmos, and Desmos is an online graphing calculator, and it can do piecewise functions. It just writes them in the reverse order. So because if a computer has to calculate this function, first it has to check this, and then it does the formula, which is what we do when we do it ourselves on paper. And strangely enough, mathematicians don't write it in that order, but whatever. So this one, I would type x is less than or equal to 0, and then I'll do a colon. So it says x is less than or equal to 0, and then move on to x plus 1. And then I'll do a comma, and I'll do the next one. X is greater than 0, and I'll move on to 2x. And that's what it looks like. So for all of the numbers over this side, it's the same as just x plus 1. And for all the numbers over this side, it's the same as 2x. So there's x plus 1, and there's 2x. X plus 1 is this blue line here. And we only want the part where it's less than or equal to 0, so we chop it off and just have this bit. And this green one here is 2x, and we only want the part where x is greater than 0, so we chop that off. And now my function is made of these two pieces glued together. If I was in the Maths Learning Centre doing this, I could probably do it here, and had scissors, I would actually draw them and cut them out and throw the bits away and join them together. That's how to draw a piecewise function. So to draw it, because you won't have Desmos in your exam, of course. So when x is less than 0, it's x plus 1. Y equals x plus 1 has a slope of 1 that goes through 1, so it looks like this. But we only want this part, where x is less than 0, and 2x is like that. And traditionally, sorry. I've just copied it. That was x plus 1, and that was 2x. And traditionally, you put a filled-in circle if it includes that point, and a not filled-in circle if it doesn't. Because 0 is in this first half, and so it has this as its function value. That's a piecewise function. And there is one particular piecewise function that you know that doesn't look like a piecewise function the way it's written, and it's the absolute value function. So the absolute value of x, its graph looks like a piecewise function. It has different formulas in different places. This is y equals minus x, and this is y equals x. And so we get that we can do this. It's y equals minus x when x is negative, and it's y equals x when x is positive. So it's a piecewise function already. It's just that we have a symbol for it all by itself, so we don't have to do this stuff. And you knew it was piecewise because when you describe to people what to do when you do absolute value, you say, well, remove the minus sign if there is a minus sign. And so it has different formulas for different kinds of numbers because you do nothing if it's positive and you take away the minus sign if it's negative. So yeah. So it's already a piecewise function. Okay, one more thing. I would like to create piecewise functions from piecewise functions. So, nothing up my sleeves. Okay, so here are my two functions. I've just copied the ones I've already got, except I called this one g before it was f. Okay, so what if I wanted to do this? Oh, no. I'm completely going to change my mind. I'm going to switch this one over at 1 instead of at 0. Okay, good. So f of g of x. So that says that if I put something into the x here, first I'll do g and then I'll do f. All right. Okay. All right. Well, to do g, I'll get different answers depending on whether x is more or less than 1. This is hard. I do not like it, Sam, I am. Let's see. I have put g of x inside f of x, so it'll totally be this. Can certainly do that. And so that means it'll be the answers from g of x, but absolute valued. Like that. So I took, these are where the answers from g of x are, so I've absolute valued those answers. Okay. Does this help me? I don't know. Well, just a second, I can do some other tricks. Since x is greater than 1, this number's positive, so the absolute value doesn't do anything. That's good. And this one, well, I suppose I could totally draw the absolute value of x plus 1, but it would be cool if I could try and figure out where that formula crossed over. So I'm just going to pull this out and think about it. So this would either be minus x plus 1 or plus x plus 1, depending on what x plus 1 was, because that's how absolute values work. And it would be minus x plus 1 if this number was negative, and it would be plus if that number was positive. Yes, let me just talk that through again. The absolute value of something is negative what it was, is minus what it was if the thing you put in is negative. The thing I put in is x plus 1. Okay. All right, so I've just moved these minuses, these ones over the other side of them. Okay. Right. So this thing, it's this thing up until x is equal to 1. Okay. So therefore my f of g of x was minus x minus 1 if x is less than negative 1. X plus 1 if x is greater than or equal to negative 1. Only this next one starts when x is 1. And 2x. Okay, so this one is greater than or equal to negative 1, but it only goes up to 1. All right. I don't know, this is not a method that I was trying to show you. I was just making this up on the spot and seeing what sort of strategies I would use to attack it. It's not necessarily a good idea to sit and try and remember exact methods to do most of the things that I show you. It's good to try and think about the decision-making processes I made. So let's go back and have a look at what I did. I had these original functions and I figured out what I had to do, and you'll notice that I tried two things. I tried thinking about what g of x did and trying to put that into here. That was hard, and so I just thought, well, I've just put g of x in the place where x goes, so I'll just do that. And then I thought about what it meant to do the absolute value of this function, which means I absolute value all the answers. And I just started working my way through what each of these two different pieces meant so that I could figure out what happened after that. And then there was a final decision over here when I glued them together, in that this one actually, this function only goes up to x equals 1, because that's what this bit said. And so this bit, damn it, you just see it all at once. And so that's why this one only went up to 1, because the 2x starts when x is 1. Okay, that wasn't pretty, I'm sorry. I wish it were. But joining two piecewise functions together in that way is one of the hardest things that you can do algebraically, because it's totally a maze of logic back and forth. If you want to talk more about it, feel free to drop into the drop-in centre and we can chat about it as long as you like. So the next thing was, in this same section, was about trig functions and their inverses. Okay. And their derivatives of their inverses, if I understand that correctly. Oh, crap. Not too bad. Okay. I just moved my page up without hitting the machine. I really should have done that an hour or two ago. Okay, inverse trig functions. Do you know what? I'm going to start on a new page. Nah, I can't. So, inverse trig functions. So, I said this way back in the complex numbers bit. Tan inverse is only able to produce one answer at a time. So, the idea of inverse functions is they undo other functions. So I can say, for example, that sine of pi on 6 is a half. It's one of the ones I happen to know off the top of my head. And so I would like to say that pi on 6 is sine inverse of a half, because that's how inverse functions are supposed to work. I'm supposed to be able to go, well, from pi on 6 to a half, I could use sine to do that, and to come from a half back to pi on 6, I could use sine inverse to do that. So I'm supposed to be able to do that. But the problem, pardon me, is that sine of 5 pi on 6 is also a half. Because sine repeats itself. Okay, every you know, if it has certain values here, then in the next lot of pi on 2, it has the same values but in reverse, and then another pi away from that, it repeats those answers again. And it just keeps repeating its answers over and over and over. And so I can't do this. I'm about to cross this out. But I could try and do this, right? But then sine inverse of a half would have to have two answers. And it can't be a function if it has two answers. If I asked a calculator, what's sine inverse of a half, it can only give me one answer. And so we have to choose which answer it's going to give. And it's not going to be this one. It's going to be this one. So I have to choose which answers my inverse trig functions are going to give. And then if I want the 5 pi on 6, I'm going to have to tell my reader in some other way to adjust it. So you say, is that because it's not within the domain of minus pi on 2 and plus pi on 2? Yes, because minus pi on 2 to plus pi on 2 is exactly the zone that we choose to be the answers from sine inverse. So we have to choose a range of possible answers it could be. And so I choose for sine inverse of something to be between minus pi on 2 and plus pi on 2. And I choose for cos inverse of something to be between 0 and pi. And I choose for tan inverse of something to be between minus pi on 2 and plus pi on 2 as well. So I deliberately choose those as my zones, and those ranges of angles cover all the possible values of sine that could come out of sine. The reason I choose those is that it makes a good sense for sine inverse and cos inverse and tan inverse to work on the angles from 0 to pi on 2, because they're the ones that fit inside triangles. And then I need to choose to extend that to the negative answers without making a hole in my domain. And so the sines have to go this way and the coses have to go this way. So in my head it's actually like this. So sine inverse produces angles in this zone. Cos inverse produces angles in this zone. And tan inverse produces angles in this zone. You will notice a rather pleasant coincidence in that sine inverse produces its angles in the place where cos is positive. Cos is positive over here. And cos inverse produces its angles in the place where sine is positive. And that's extremely convenient for doing derivatives of inverse trig functions. All right, so what that means is that when you do sine of sine inverse, you don't always get the answer you started with. So if I did just some examples, cos inverse, cos inverse of a half is a perfectly reasonable thing to want to calculate. Cos inverse of a half is pi on 3. And cos of pi on 3 is a half. And they neatly cancel each other out. Cos of cos inverse, cos of cos inverse of a half is just a half. They cancel each other out. That'll always happen. If the cos is on the outside and the cos inverse is on the inside, they'll always cancel each other out. But if I did this instead, lost my pencil. Of course, my pencils choose not to sharpen properly at this time. That'll do. Okay, so cos inverse of pi on 3, totally going to be fine, because pi on 3 is in the correct zone. So this will be cos inverse of half, which is going to be pi on 3, and everything's lovely. Okay, the answers from cos are between 0 and pi, and that is between 0 and pi, and that's fine. And so they cancel each other out. But cos inverse of cos of 4 pi on 3 is not going to turn out that way. So 4 pi on 3 is here, because 3 pi on 3 gets me to here, and then 1 extra pi on 3. And so cos of 4 pi on 3 will be the same as cos of pi on 3, only negative. Whoop, not quite ready yet. It will be cos inverse of minus a half. But cos inverse of negative a half, I'm only allowed to use angles that are in this top half. And so this will actually be 2 pi on 3 and not 4 pi on 3. A simpler example to make sure that we've rammed this home. Cos inverse of cos of minus pi on 3. Well, cos of minus pi on 3 is the same as cos of pi on 3, and so that'll be cos inverse of a half, and cos inverse of a half is plus pi on 3. So, just to make sure we get this, cos of cos inverse will always cancel each other out. Cos inverse of cos will not cancel each other out exactly. It will give you whichever angle is in the correct zone that produces that same answer for cos. And sine similarly, and tan similarly. Now we have something rather interesting. What if we did cos of sine that's a whole other thing. Cos inverse of sine or cos of sine inverse. I think I'm going to do cos inverse of sine of x. Let's see if we can simplify that. Okay. So it's totally not going to be x. Like if it was cos inverse of cos x, we had a chance that it's going to be x. But it's not going to be x in this case. Oh, for the sake of Frel, it's supposed to be this way around, sorry. Sorry about that. The other one's going to be really weird. This one I can do. So cos of sine inverse of x. Okay, well, cos of cos inverse of x would just be x. That'd be great. But this is cos of sine inverse of x. So this is hard. So I have to take a number between 0 and 1, find out what angle gives it that sign, and then do cos of that angle. All right, this is too hard at the moment. And so mathematicians, one of the mathematicians' ways of dealing with too hard is to give things names so that they're easier to talk about. I am going to call this by theta because it's an angle. All right. And now I know if I do sine like that, I know always that sine of sine inverse works. That's always true, just like my cos of cos inverse always cancels out. Okay, because sine always produces a number between plus and minus 1. I started with numbers between plus and minus 1. I should be able to get back to there. Oh, that's interesting. So if sine inverse x is theta, then sine theta is x. That makes sense. That's what inverse functions are supposed to do. And so the thing I'm trying to calculate is cos of theta. I want cos of sine inverse of x, which is cos of theta. Okay. But cos theta and sine theta are related because I know that cos squared plus sine squared is 1. So this is the square root of 1 minus sine theta squared. Magic trick. So I can say cos theta squared plus sine theta squared is 1. That's where I got this information from. But sine theta was x. So I sub that in. Yay! So therefore cos of sine inverse x is root 1 minus x squared. Fabulous. There is something that happened here that is extremely important to point out at this time, and it was right here when I did this square root. Technically, cos theta is allowed to be negative, right? So it really should have been plus or minus, but it can't be both plus and minus because that doesn't make any sense. So how do you choose which one it's supposed to be at any moment? But it's very convenient because theta came out of sine inverse. That means that theta is in this zone. And cos theta is positive there. And so I don't have to worry about the plus or minus. That is one of the reasons why we chose the zones the way we did, so that that happened. Therefore, cos theta is positive. And so that is the reason why this came out to be a plus. I'm sure I could have made this working a little easier by giving a name to cos of sine inverse of x as well. In fact, if I was doing this again, I would probably extend this part of the working a little and actually do this. Just bear with me. I would go like this. I would go, now, cos theta squared plus sine theta squared is 1. And so cos theta squared plus x squared is 1 because sine theta is x. And so cos theta squared is 1 minus x squared. So cos theta is root 1 minus x squared. But theta is in the zone from minus pi on 2 to plus pi on 2. And so therefore cos theta is positive, and so therefore cos theta is actually just right. So I did a plus or minus there and go, aha, but it's positive, so therefore it's the positive one, and so therefore cos of sine inverse of x is just the positive one. Right. Yay. The notes here will be on the Maths Learning Centre Maths 1M page eventually, but just letting you know. All right. Oh, wow. Okay. Cool. We're going to have to stop soon so people won't want to use the room. So when you do derivatives of trig functions, this exact thing happens. So derivatives of inverse trig functions. Because let y be sine inverse of x, and we want to find the derivative. Well, let's see. X is equal to, so y is equal to sine inverse of x, and so that means that sine of y is equal to x. And now if I differentiate both sides with respect to x, I will get cos of y times dy and dx is 1 when I differentiate. Do d on dx. This one's here is because of the chain rule. But look, we've got the same deal here. Sine of y squared plus cos y squared is 1. And so x squared plus cos y squared is 1. Cos y squared is 1 minus x squared. Cos y is plus or minus root 1 minus x squared. But actually, it's only just one of them because the y, because y is sine inverse of x, and therefore it's in the zone where cos of y is positive. And so therefore we get root 1 minus x squared dy on dx equals 1. So therefore dy on dx is 1 over root minus x squared. I am going to fix that. And you'll notice in the book it says that the derivative of arcsine is 1 over root 1 minus x squared. Oh crap, your lecturer uses arcsine instead of sine inverse. Sorry about that. I should probably go back to the beginning of my notes. These are yours. When I started talking about this and say note, sine inverse is arcsine. The reason they use arcsine there is that a computer, you can't type sine inverse in the same way, especially older computers, and so they needed a name for it that you could just type in as a name. An arc sine is a good one. An arc means length of arc, which is what radians do when they measure angles. So, yeah, that's why it's called arc. Thank you. Maths Learning Centre is open all the way to the end of the exams. This video should be up at some point by the end of tomorrow. I will email you all when it's ready. Thank you. You're welcome.
I just had a question. I understand that you can't give an answer that's outside of the zone. I'm not really sure how you came to that answer.
Oh yes, let's do that. It is still recording, so we can actually put that on the recording. So we were here. Okay, I'll just pop that at the end. See note. Okay, note. Okay, so we know that our problem is because so cos inverse of minus a half is where we were.
Yeah.
And we want to know what that was. And we know that one option is 4 pi on 3. But we want the option that's within 0 to pi. And you're saying, how did I figure out it was this one? Yeah. Okay. So I know that cos is the x-coordinate. So I need something over here that has an x-coordinate of minus a half. That's what I want?
Yeah.
And by symmetry, it will match with the angle over here that has an x-coordinate of a half, which is totally not drawn correctly, I'm sorry. That has an x-coordinate of a half. So cos inverse of minus a half will be this part of the angle here will be this part here. Yeah. Right. So let's just see. Cos of whatever this is supposed to be a half, this angle here. And that is 60 degrees. But the angle I actually want is this one. That gives me over here. So the actual angle I want is going to be pi minus that.
Yes.
And pi minus pi on 3 is 2 pi on 3. Because it's 1 minus 1/3. It's 2/3.
Right.
That's the long version. So cos inverse of minus a half.
So negative a half is outside of it, so you changed it to a half?
Well, it's just because my drawing was easier to do. Like,
It's the same, it's just the reverse, like flip side of it.
yeah, so the idea is that cos of an angle over this side is the same as cos of an angle over this side, except these ones are negative.
Yeah. So I tried to draw it myself, and like 4 pi and 3, would that be
Yep.
down here?
Mm-hmm.
And then
Oh,
you
and that's
just
totally quicker.
flip it to,
I totally did that. That's exactly what I did. It was here.
yeah?
I flipped it up here because
Yeah.
that's where it needs to be.
Yeah.
You want to match your x-coordinate
Oh.
because it's the cosine.
Yep.
So match the x-coordinate. Yep. And this was 4 pi on 3, which meant that this bit was pi on 3.
So it's just
Which
going to
means that
rotate
this bit is
anti-clockwise
pi
by 90 degrees.
No, it's flipping upwards.
Oh, okay.
So if I had cos inverse of minus root 3 on 2,
Yep. Something a little nicer.
if I had cos of cos inverse of cos of 7 pi on 6, right? That'd be, now 6 pi on 6 would be here, and a little bit extra pi on 6, so it's there. So I'm going to flip that up here. And so it was an extra pi on 6 here, so it'll be just short by pi on 6 here. So that'll be 5 pi on 6.
Okay. And so if it was over this side, it would still...
It would flip up.
Yep. Okay.
So yeah, if this was like, so by the same reasoning, cos inverse of cos of Right, oh man, no, just a second.
Oh, I just realised I'm not actually confused.
11 pi on 6 of 11 pi on 6.
Yeah.
That'd be over here.
Yeah.
And so the matching angle up here is just pi on 6.
So it's just much easier to flip it if you know what the unit circle
Yeah,
is like.
exactly.
If you don't, you have to do that.
This sort of thing. Yeah.
Wait, why are we flipping it again?
Oh no, because we're cancelling out something that when we do cos inverse of cos, you can only get answers that are between 0 and pi.
Alright.
When you do cos inverse of cos, you can only do answers that are between 0 and pi. So the answer is totally not going to be 11 pi on 6. It has to be the matching angle in this zone. And so we flipped it above because that has the same cos, because it has the same x coordinate. If we were doing sine inverse of sine, then we'd flip it this. Then if we were doing sine inverse of sine, we'd flip it that way.
Oh, that's if you're doing inverse cos of cos.
Yeah.
And then if it was just cos of inverse, then you could just strip
Yeah, just
away.
cancel them out.
Alright, and you want, yeah, because you want the same x coordinate.
Yeah.
And you just flip them up. What's the pi on 3 bit like? Is it I know that's pi on 3 from here.
Yeah.
But do we not regard this angle?
Oh yes, that's what I was looking for. It was actually 2 pi and 3 that I wanted. But it's pi and 3 this way, so this way is 2 pi and 3.
Oh, okay. Yep. Alright.
All right, I'm hoping I'm not going to lose my pieces there. Where's the rest of this? Ah, there it is.
Thank you very much.
You're welcome. That's what I'm here for.